So in this series of videos, we're going to be talking about continuous probability distributions. So probability distributions for continuous random variables. Let's first talk about the probability density curve. Now suppose I have a data set with a continuous variable, right? And I want to construct a histogram for that variable. So a histogram with 5 bins or 5 intervals looks something like this, right? So it seems like according to this histogram, we have a mode in this range, right? So let's suppose I want to trace out the tops of the bins. So let me do that. My curve would then look something like that. So nothing too fancy now. Recall that when we discussed histograms in the past, we said that one thing we can do to improve the histogram is to increase the number of bins or the number of intervals. Right? So here I have another histogram with double the amount of bins. Notice that this histogram shows us that there are two modes, one here, right, and then one about here. So just by doing that, the histogram already helps us understand our data better. Right? Let me also trace out the tops of the bins. So do that. And again, my curve would look something like this. Suppose I continue to increase the number of bins. Right? Here's one example. Note that my curve has become much smoother. Right? And suppose that we could increase the number of bins to a very large number. Then the curve that traces the tops of the bins will be perfectly smooth. Right? Such a curve is what's known as the probability density curve. So probability density curve. So let's give a formal definition of the probability density curve. So the probability density curve is the curve obtained by tracing the tops of the bins of a histogram. Right? When the number of bins is very large. Okay. Now we can also define the probability density function. Right, or PDF as the function that produces the probability density curve. Now, at this point, you may be wondering, why do we even care about the probability density function and the probability density curve? The answer is we care about those two concepts because of the following definition. So we have a definition regarding probability. So the probability that a continuous random variable falls between two values is defined to be the area under the probability density curve the area under the probability density curve between those two values. So now let's look at an example to make sense of this definition. Suppose I have the following probability density curve. Okay. And suppose I have 2 points. Right, let's say this is my I have the variable x, and suppose I have 2 points x1 and x2. So let's say x1 is here, and then x2 is over here. Okay. Then the area under the curve between those two values, which is the shaded area here, is the probability that the variable x falls between x1 and x2. So that's the probability that x1 is less than or equal to x, less than or equal to x2, okay? By definition. And that's why we need to understand what the probability density curve is and what the probability density function is. Now this definition has a very important implication. Which is that the probability that x is equal to a particular value x sub 0, x sub k, is always 0. This is always true, right? And x here is a continuous random variable. Okay. Let's actually see why this is. Now, I can write the probability that x is equal to xk as the probability that xk is less than or equal to x, less than or equal to xk. Right? And suppose that xk on this graph is right here. So this is my x sub k. Now by definition, right, this probability is the area under the curve between xk and xk. But if you look at the that area on this graph right here, we only have 1 point, so there's no width. Right? So no width under the curve, and so the area is equal to 0, and so the probability that x is equal to xk, which is equal to the probability that xk is less than or equal to x, less than or equal to xk, is 0. So what did we do in this video? In this video, we talked about the idea of a probability density curve and a probability density function. Then we define probability for a continuous random variable, and then we reach a very important conclusion, which is that if x is a continuous random variable, the probability that x is equal to a particular value, x sub k, is always 0.